Physics 2212, Lab 5, magnetic braking with Faraday's law. So introduction, key ideas and formula, Ohm's law, magnetic field on a loop, magnetic flux, moment principle, Lenz's law. On the left is the diagram and data. So as you can see, there's a bar magnet and it was dropped through a tube, and the tube was it was made of aluminum foil, so it was wrapped up. And what happens is there's an induced magnetic field that pushes against the magnet and slows it down. So if it's dropped without being in the tube, it's a lot faster than when it's in the tube. The physical experiment, we got an average of about 1.192 seconds, and the code experiment, we got 0.941 or 0.943 seconds. Why can't we use a Ferris tube, for example, a steel pipe? A Ferris tube has iron in it, which could cause it to become an induced magnet. If the tube is magnetic, then it could affect the results of our experiment. What happens to the magnet? How does this compare to a magnet falling in free space without a tube? The magnet was slowed down by the tube. When it was dropped outside the tube, it fell a lot faster. Here's some of the code. So step 1 was to plug in the values that we had measured from our experiment. And then step 2 was to make a function to calculate the magnetic field of the bar magnet, and that's seen using the formula to the right. And then the next step was to create a function to calculate the magnetic flux, which is seen to the right and below. And step 4 was to calculate the current in the ring, and the ring in a current is just delta flux over the ring's resistance. And then steps 5 and 6 were to calculate the B field in each ring, and that was done just using the formula to the right. Step 7 was to calculate gravitational force, and gravitational force is just mass times gravity in the negative y direction. And then calculate net force, you just add up force of gravity and force of the magnet. And then step 8, magnet's velocity and position, and that's just done using the two formulas to the right. The computational model. So this is what was printed out when we ran the experiment. The velocity versus time graph is shown up there, and it shows how the velocity of the magnet starts out, and it's very steep, and then it evens out, and it's not increasing, it's just going at the same rate, and then once it's out, and then the amount of time that it took to go through the tube in the code was 0.943 seconds, but the actual time was 1.192. And there's a lot of reasons why this could have happened. One of them is air resistance. Another one is it was people measuring the time, and so there could have been something wrong in that. Discussion questions. The intensity of the coloring in the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current? Which one counterclockwise? So red is clockwise, but blue is counterclockwise by Lenz's law, because the magnet would not slow down if it was the other way. What happens to the dynamics of the system when you flip the magnet around? The current would be in opposite directions, but it would still take roughly the same amount of time. How does the total time in tube of your real world system compare to that of your computational system? So it was a little different. If a machine measured the time, it would have been more accurate, and also we didn't take into account air resistance. What does this shape of the velocity versus time plot tell you? The force is acting on the bar. The force starts unbalanced and then reaches balance, and the speed stops changing, as you can see in the graph. What if questions? What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The force of the magnet would be much greater and could possibly counteract gravity. Holes or slots were cut into the tube. How would this affect the rings in your current model? The braking force would decrease because there'd be less flow of current through the tube, which makes sense because the current wouldn't be able to flow as freely. And conclusion, this lab helped me to grasp a better understanding of Faraday's law and its applications, as well as understanding current and EMF changes from magnetic flux. This is by far my favorite lab experiment because it helped me to not only understand the concepts, I had fun in doing so.